Good morning, good afternoon, ladies and gentlemen. Welcome to another series of online lessons. Now, in today's lesson, we are going to look at Jacobian determinants. If you haven't already, please subscribe to the channel and leave a like and comment on what you'd like to see in the next lesson or your concerns. Comment. Now, as I said, basically, I'm just going to show you how to construct a Jacobian matrix. So basically, if we have functions, let's say two functions or three functions, f of x, y, z, g of x, comma, y, z, let's say, k of x, comma, y, comma, z, then basically the Jacobian of f, g, and k simply equal to the partial derivatives of the three functions, which is x, comma, y. I mean three functions, which is f, g, and k. So that is f, g, and k. And with respect to the variables x, comma, y, comma, z. Okay, so you should make sure that if you have three functions there, you also have three variables. So you should check the variables that are in the functions. So total, there are three variables x, y, and z. So meaning that there should be three functions or three functions and three variables. This is because the determinant of a matrix only exists for square matrices. So now this is simply equal to f with respect to x. So this is the determinant of f with respect to x. And you say f with respect to y. Then you say f with respect to z. So you finish f with respect to all these will be the first column. Then for the second column will be g with respect to x, so g with respect to x, g with respect to y, and g with respect to z. And finally k with respect to x, k with respect to y, and k with respect to z. So basically, this is the Jacobian of f, g, and k. So same implies if we had two functions. So if we had two functions f, if we had two functions, let's say g, x, comma, y, and f, x, comma, y, the Jacobian of g and f will simply be equal to the partials of g and f with respect to the two variables x and y. So which will be equals to g with respect to x. And here, not the order doesn't matter. You can start with f, you can start with y, you can start, but the consistency should be inside here. So if it is g with respect to x, then g with respect to y, then again f should be with respect to x, and f with respect to y. So the consistency in here is what matters the most. So basically that's it. So that is how we construct the Jacobian matrix and the determinant. So from here we need to calculate the determinant. So you have knowledge on how to calculate the determinant for 3 by 3 matrices and 2 by 2 matrices. So let's look at an example. So again, here you're given x is equals to r cos theta and y equals to r sin theta. Find the Jacobian of x and y. So we know that the Jacobian of x and y, which is j of x comma y, is simply equal to the partials of x and y with respect to the variables that we have. So we have r theta, r theta. So we have two variables, which is r and theta. So this will basically be equal to x with respect to r, x with respect to theta, y with respect to r, and y with respect to theta. Okay, then from here we simply find the derivatives. So x with respect to r, we are differentiating this with respect to r, so we're just differentiating r here, which will just be cos theta. X with respect to theta, differentiating x with respect to theta, so r is a constant, so that is r, that will be negative r sine theta. Okay, then we're also differentiating y with respect to theta. Let's start with y with respect to r, the order y with respect to r. So y with respect to r, that is giving us sine theta. Y with respect to theta, that is giving us r cos theta. So from here, we just replace in the matrix. So Jacobian of x and y will basically be equal to r with respect to x, which is, x with respect to r, which is cos theta, x with respect to theta, which is negative r sine theta, y with respect to r, that is sine theta, and y with respect to theta, that is r cos theta. Then this is a 2 by 2 matrix, so we just multiply the measures minus the minors. So this times that will be r cos squared theta minus the minors. So this times that will be negative r sine squared theta. Then this and that will simply, we factor out r. So this is r factored out. Then we have cos squared theta. This and this will give us plus sine squared theta. So basically, we know that. So let me just put that. This was an assignment. You just say but cos squared theta plus sine squared theta is equal to 1. So this would be 1. And what we're going to have as our Jacobian of x and y is just r, because 1 times r will simply be r. So that is basically it. So that is the first example. Let's give a try to the second example. All right, so we have this simple question here. So it asks us to find the Jacobian of r and theta, given that x is equals to r cos theta and y is equals to r sine theta. So basically, we see that this function as r and that function as r. So we don't know which r, but basically this is the partials of r and theta over, we don't know what to put here because we have two functions here. So r is here and r is there, theta is here and theta is there. So it is very difficult for us to put variables there because we don't know what we're differentiating with respect to. But what we can do in this case is we can make r subject of a formula and theta subject of a formula by combining these two equations, so that we have one equation that has r and one equation that has theta. So how are we going to do that? So first things first, we're going to square both sides of these equations. So squaring both sides, we're going to have x squared is equals to r squared cos squared theta. And here we see that we're going to have y squared is equals to r squared sine squared theta. And basically, if we add these sides of the equations, because cos squared and sine squared is equal to 1, we're just going to remain with r. So we're saying adding this and this, we get x squared plus y squared equal to adding this and that, we get r squared cos squared theta plus r squared sine squared theta. And basically factoring out the r, we have r squared cos squared theta plus sine squared theta. We know this is equals to 1. So basically what we have is r is equal to, let me just write here. So basically r is equal to the root of x squared plus y squared. So we multiply half to the powers, and we get that. And now we need to find the expression for theta. So this is the expression for r. We don't have any uh, theta here, so it's going to be easy. So we know that r can be with respect to x and y. So this is how our Jacobian will be. So same applies for with finding the expression for theta. So for theta, we are going to say, we know that if we say y over x, this will be equals to r sine theta over r cos theta. And basically the r's will cancel out and will remain with a function that will only have theta and x and y in it. So we know that sine theta over cos theta is simply equals to tan of theta, and this is equals to y over x. All right, so we also have an expression for theta. So basically we have you can say y, let me just say y is equals to x tan theta, and here we can say it's just the same equation. I'm just making subjects of a formula in advance, saying x is equals to y over tan inverse, tan of theta, sorry. So y is equals to x is equals to y over tan theta. Okay, I've just done that for simplicity, but simply we have two equations here, and the Jacobian. So now let's say the Jacobian of r and theta, which we said is equals to now r theta with respect to x and y, which is equals to r with respect to x, r with respect to y, theta with respect to x, theta with respect to y. Though I'll show you a simple method of doing this, but I want you to know this so that in case you are required in the examination. So now we need to find r with respect to x. So r with respect to x, this is basically, we have r, which is x squared plus y squared to the power half. And how we differentiate this, let me put it in brackets. I've put a prime there to show that we're differentiating. So how we differentiate, we drop the power. So this is half. We differentiate what is inside with respect to x. So that is times, which is 2x. Then we write what is inside, which is x squared plus y squared to the power. We subtract 1 to the power. So that is 1 over 2 minus 1, which will give us negative 1 over 2. So basically the power here becomes negative 1 over 2. So simply this is equals to the 2 there, and the 2 can cancel out. We remain with x all over, because of the negative here, root of x squared plus y squared. Okay, then now we find r with respect to y. So r with respect to y, same thing. So that is half. Then we differentiate what is inside with respect to y. So that is times 2y. Then we write what is inside, which is x squared plus y squared. Then to the power, we subtract 1. So that is to the power negative half. So this simply cancels out and remain with y over root of x squared plus y squared. And basically that is r with respect to x and r with respect to y. And now we find theta with respect to x. Okay, so this is why I separated, so that I make either of them subject to the formula. So we see that theta with respect to x is very difficult to find, because when you look at the function that we have here, when we make theta subject to the formula, we're going to have tan inverse of y over x of which it is difficult to evaluate tan inverse of something. So what we'll do is, we know that theta with respect to x is simply equal to 1 over x with respect to theta. So what we're going to find is x with respect to theta here. So x with respect to theta, we know that x is simply equal to y, then tan theta is simply equal to 1 over tan theta is cot theta. So that is cot theta, which is just equal to y, then we say cos theta over sine theta, over sine theta. So theta with respect to x will be equals to 1 over x with respect to theta. So x with respect to theta, so simply putting it, this will be the denominator squared. So that is sine squared theta. Then the derivative of this, that will be negative sine theta times the denominator sine theta. Then we say minus, so this is all over, minus the derivative of sine, that is cos theta, times the numerator there, that is cos theta. So this is just differentiation, which you should know. So x with respect to theta, which is what we've put down here, and we've said that, so meaning that theta with respect to x is equals to 1 over negative 1, because when we factor out a negative here, we're going to have negative, then this times this, that will be sine squared theta, plus this times this, that will be cos squared theta, which will give us a 1. So this is simply negative 1. Then there is a y here, sorry. So there is a y outside here, so I didn't include that. So there is a y here. So y times negative 1 will simply have negative y all over sine squared theta. Okay, so there is a negative y here, which is a constant. So basically it will be y, then the derivative of what is inside here, which is simply that. Then this inverse will just be sine squared theta over y. So negative sine squared theta over y. So that is theta with respect to x. Now we find theta with respect to y. So again, it's going to be the same thing. So y, we know that y, we can write y here. We can say y is equals to x tan theta. So y is equals to x tan theta. And we know that we're looking for theta with respect to y, but it is difficult to find theta with respect to y because we'd have to make theta subject of the formula. So we can say this is equals to 1 over y with respect to theta, of which this would be equal to 1 over, so the x there is a constant, so this can be written as x, then tan theta is simply sine theta over cos theta. So the x follows outside here, then differentiating this with respect to theta, we use the quotient rule again. We say the denominator squared, which is cos squared theta. Then we differentiate the numerator, which is cos theta, times the denominator, which is cos theta plus, or minus, sorry, minus the derivative of the denominator, that will be negative sine theta, times the numerator, which is sine theta. Then basically what we're going to have is theta y will be equals to 1 over x times this will be 1. So because this is cos squared theta, this and this will give us plus. This and this will give us sine squared theta, which is just 1. So we just say over cos squared theta, of which this will be basically equal to the inverse, or flipping that would be cos squared theta all over x. Okay, so now we have our three derivatives. So let me just write them here. All right, so we'll say our Jacobian of r and theta is basically equal to, we replace, so r with respect to x, which is this, x over root of x squared plus y squared, r with respect to y, which is this one, say y over root of y squared, x squared plus y squared, then theta with respect to x, which is this one right here, negative sine squared theta all over y, then cos squared theta all over x. So again, this is a 2 by 2 matrix. Just do the usual major diagonal. So the numerator and the numerator will multiply, and that basically will give us x cos squared theta. Then the denominators will multiply, so that would be x root of x squared plus y squared, then minus the minor diagonal, so that would be negative y sine squared theta all over the denominators, y root of x squared plus y squared. So simply simplifying this, we get the x goes. So simply we see that the x there and the x goes, the y and the y goes, and simply this times that will give us a plus. So this will be cos squared theta plus sine squared theta, and the denominator will simply be the same, which is just root of x squared plus y squared. And this is simply equal to 1 over root of x squared plus y squared, because that will give us 1. Then we know that r is equals to what's that? That is 1 over, r is equals to the root of x squared plus y squared. So we can simply replace this with r. So Jacobian of r and theta is simply equal to 1 over r. So this is 1 over r. However, there is another way that would have taken, which would have been way shorter, but I just wanted us to see that we can also expand this. So the other way that we could have taken is this. Okay, so we, as you can see here, so this will be very useful in the exam because it will save you time. Here you've been asked to find the Jacobian of r and theta, okay, which is simply equals to r, I would say Jacobian, let me write it here, Jacobian of r and theta is simply equal to the partials of r and theta with respect to x and y. Okay, so simply what we could have done is, since it's difficult for us to make r a subject of a formula in here, what we would have said is this is basically equal to 1 over the Jacobian of x and y all over the Jacobian of r and theta. So basically we would have found the Jacobian of x and y. So we know that, so this would have basically been equal to 1 over the Jacobian of x and y, which is just x with respect to r, x with respect to theta, y with respect to r, y with respect to theta, which would be 1 over, we know what x x with respect to r is. So let me just zoom out. We know what x with respect to r is. That is cos theta. Then x with respect to theta, that would be negative r sine theta. Then y with respect to r, that is sine theta. R with respect, y with respect to theta, that would be r cos theta. Okay, and basically what we would have done here is simply saying this is equal to 1 over, we find the determinant, so the major diagonals, that is r cos squared theta minus the minor diagonals, that is negative r sine squared theta. Okay, and basically this would have been equals to 1 over, we factor out the r, we remain with cos squared theta. This and this will be plus sine squared theta, which basically is equal to 1 over, this will be 1, so which is 1 over r. So that would have been the other method that we should have used. So it's the same, you'll be given the same answer. So this is very important to note. So you should note that if it is difficult for you to find, let's say, Jacobian of f comma g with respect to x comma y, this is basically equal to 1 over the inverse, which is Jacobian of x and y, over the Jacobian of f and g. The same applies if we had three variables, let's say x comma y comma z. You know this with respect to, let's say, f, g, and k. So basically this is equals to 1 over the Jacobian of, starting with f, g, k, then with respect to x, y, and z. So this is something that you should note, and I hope you use in the following 3 examples that I'm going to give. So I have 2 questions here. I'm going to add one more. So given that x is equals to r sine theta, y is equals to r cos theta, find the Jacobian of x and y and the Jacobian of r and theta. Then secondly, given that, so copy this, you can pause the video, you copy that. Then secondly, given that u is equals to that and v is equals to that and w is equals to that, find the Jacobian of that. Then lastly and finally, given that x is equals to p sine a cos b, y is equals to p sine a sine b, z is equals to cos a, find the Jacobian of x, y, and z. So this is it for tonight. Have a good evening.